Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
All right. Now, I just want to give you a look into the future. Okay, now, we're getting there. We have X and Y. We have the horizontal position of the proton, and we have the vertical position of the proton with respect to that central trajectory. Now, you remember when I said that in physics, to know where an object is, whether it's a proton, whether it's you or me walking down the street, whether it's a black hole, you need to know the position and the velocity. All right, so we got the position, X and Y. We need to know what would you'd call the velocity in phase space, okay? And that's the amount that the proton's position is changing with respect to how far it goes down through that quadrupole. Not time, but S, okay? So these equations right here, that's what they're talking about. And you got more trigonometry. You got the sine, the cosine, the sinh, and the cosh, all right? So I, again, think, you know what, let's go a little bit more, but we'll recap when we pick up next week. This is a diagram I did to try to physically show what in phase space, when you're talking about the position of the proton as it circulates around the booster synchrotron, in phase space, I tried to draw a representation of its position in the x-axis, the horizontal axis, the y-axis, the vertical axis, and the z-axis into the page, okay? And then I said, as I said, X prime and Y prime represent how much its position has changed, okay, in the horizontal direction and in the Y. And you can see these equations. These are differential equations. X prime is equal to the derivative, the change of the proton's position in the X direction with respect to its distance along the quadrupole magnet, okay? And then you got some trigonometry going on. And likewise, the change in its vertical position in phase space with respect to its distance along that central trajectory, S, ds. So you got ds, dy with respect to dx. You see the similarity. Now we have the dependence of the proton in the horizontal and the vertical direction with respect to their central trajectory. We have its dependence upon how far it travels through that quadrupole magnet, not time. We have it with respect to S, okay? And we got more trigonometry, all right? So Now, here's another schematic that I drew. And again, it tries to express what we've been talking about. All right? Okay? And so now, because I really want to get to those equations of motion, let's just go down here. All right? Some substitutions were made. We had to do some boundary value problems, which basically is using initial conditions to arrive at values for the different constants, okay? All right? All right? So I want to focus in on these four equations, okay? All right. We have x is equal to the initial value of x, the horizontal position of that proton in phase space, times the cosine of the square root of a constant, okay, called the force constant. And we're going to get to that in a little bit. Just remember, K is the force constant. And I want to show you what that means in physical terms, okay? Times the distance along the z-axis, the trajectory of that proton through the booster synchrotron, plus the change in the horizontal position with respect to the z-axis divided by the square root of that constant. Oh, I know you're loving this. Okay. Times the sine of the square root of that force constant times the distance s. Okay. As much as I know you're digging this, let's try to minimize the pain here, shall we? All right. Okay. So these other equations, what they simply represent in terms of trigonometry, using sines and cosines, sinh and cosinches, is trigonometry. But what these four, and I want to reduce the pain, so I was not going to read out the other three in English, but I think you get the point, okay? But these four equations, x equals to this, x prime, which is the change of the proton's trajectory in phase space in the horizontal direction, left and right, with respect to that central trajectory along the z-axis through the quadrupole magnet, okay? That's what that represents, okay? It's like a velocity, but not with respect to time, but with respect to distance along the z-axis, okay? And the same thing for the vertical position of that proton in phase space, up and down with respect to that central trajectory. This equation expresses its position and its change in position with respect to how much is gone along the x direction, the z direction, right through the quadrupole magnets. Okay, so we have arrived for the motion of a proton circulating around a synchrotron. Mathematically, we have been able to identify its position in phase space, which is the horizontal and vertical position of it with respect to that central trajectory. Not with respect to time, but with respect to S, that trajectory down through those quadrupole magnets, okay? So now we know at any point, we know where the position of those protons are in phase space, in the horizontal direction, to the left and to the right, and in the vertical direction, up and down, with respect to that vertical axis, okay? So, we have the equations of motion for protons undergoing betatron oscillations as they circulate around the booster synchrotron. Now, this next part here, oh, we're going to get to that next week, all right? It's a matrix. And we're going to find out what that's about, okay? All right. In summary, we have seen how we use mathematics to change reference frames for the protons circulating around the booster synchrotron at Fermilab, okay? We went from describing their position and their velocity with respect to time to describing their position and their velocity with respect to their trajectory through the quadrupole magnets. Mathematics, everybody, tools, analytic geometry, combination of algebra and geometry, calculus, trigonometry, differential equations, boundary value equations, okay? Tools, all right? So we are now at the point where we have been able to mathematically describe the position of a proton and how fast that position is changing. We have been able to identify the equations of motion, which in a practical way help us to keep that beam of protons as they are accelerated energetically as they travel around the synchrotron. Keep them collimated so they do not start to collide with the sides of the quadrupole magnets. Now, again, this motion is described as betatron accelerations, okay? As the protons are accelerating around the synchrotron, they experience perturbations. And you know I want to use that word. They experience perturbations in their motion, up, down, left, right. And those equations that I showed you, the equations of motion, they're equations of simple harmonic motion, a spring oscillating up and down, okay? Again, in nature, it's amazing that we have mathematical equations that describe these phenomena. So, I want to show you a diagram of simple harmonic motion. And keep in mind, that's what the protons are doing as they're circulating around the synchrotron. They're bouncing back and forth, up and down, left and right, along that central trajectory, like a spring. Okay, here we go.